Hello everyone and welcome back to Introduction to Number Theory. In this video, I would like to show you an interesting application of Kroneker's theorem. We all know trigonometry, and there is a remarkable sine function in trigonometry. And in number theory, we mostly deal with integers. What if we try to put those two together? The sine function of integers. Here you see a set of values of the sine function on positive integers. What can we say about these values? Well, for instance, we understand that sine of a positive integer will never be equal to 1. We understand that the sine function of positive integer will never be equal to 0. We understand that the sine function of a positive integer will never be equal to -1. Well, the first and the third properties also hold for the sine function of whole integers, not only positive. Well, the sine of 0 is equal to 0, so if n is just an integer, then value equal to 0 can be obtained. And the question is, okay, so these three values will never be obtained by a sine of a positive integer. But how close can we get to value 1? How close can we get to the 0? How close can we get to the -1? And in general, how close can we get to other elements of the segment -1, 1? Well, we understand that all values of the sine function are inside this segment. And what about other values? Well, we understand that there are infinitely many, but certainly not all of these values that can be obtained as a sine function of a natural number, of a positive integer. And the Kroneker's theorem answers the question, how close can we get to 1 or -1 or 0 or any other number from -1 to 1? Well, recall the trigonometry circle. And here we have the beginning of this circle. And the length of the circle is actually equal to 2 multiplied by pi. And this is point 0 on the circle. And somewhere over here we have point 1 on the circle. And here we have point 2 on the circle, and 3 on the circle, and 4 on the circle, and 5. Well, I am actually not sure whether it's over here or over here. Let's write it, I suppose here. 5 on the circle, and 6, and so on. And these are positive integers on the trigonometrical circle. Does it recall anything to you? Indeed, it's just like a grasshopper with step equal to 1 jumping along a circle with length 2 pi. Well, we know the Kroneker's theorem that if we have a circle of length 1 and an irrational grasshopper, which means a grasshopper with an irrational step, then its trajectory on the circle will be dense, which means that the grasshopper gets very near, arbitrarily near any point of the circle. And here we have a similar situation. And we need to understand that all that matters is the proportion between the length of the step of the grasshopper and the length of the circle itself. So 1 over 2p is the proportion between these two lengths. And all that matters, so that we could apply Kroneker's theorem, is that this quotient is irrational. But we certainly know that this is so. So we can apply Kroneker's theorem to positive integers on a trigonometrical circle. And we understand that positive integers form a dense set. And from this it follows that we can get arbitrarily close to the upper point of the circle, which means that the sign of a positive integer can be arbitrarily close to 1. And we can get arbitrarily close to the lower point of the circle, which means that the sign of a positive integer can get arbitrarily close to -1. And also to this point, which means we could get arbitrarily close to 0, and so on. So the values of the sine function on natural numbers, I mean positive integers, is dense within this segment. And finally, well, let's write a statement. Say the supremum of this set is equal to 1, and the infimum of this set would be equal to -1. But the main result is that this set is dense between -1 and 1.